So this is the last stuff we have to cover in Unit 5-6. This is Box F, the intersections of two lines. And this is, again, a bit of a recap of stuff that you first encountered way back in grade 10, when you did intersections of lines and you solved linear systems. So you had two equations, each one represented a line, and you solved the linear system to find the point of intersection. We're going to do something similar here. So if you think back to grade 10, you'll remember that when you were dealing with lines that were, both lines were lying in a single plane, which is what we're going to look at first, we had three possibilities for the intersection. The lines could be parallel and distinct, which meant that there was no intersection. The lines could intersect each other at a single point, where you had a unique x value and a y value that told you your point of intersection. Or the two lines could be coincident, which meant they were essentially the same line and you had an infinite number of points that were in common between the two lines. Our first example here, we've got two lines that are in the same plane. So these are two-dimensional lines, so they have to be in the same plane. And we just want to find the point of intersection. So the only difference between what we had back in grade 10 and what we have here is we don't have the algebraic equation, we have these vector equations that we've been working with. Okay. So how do we want to approach a question like that, like this? First thing we want to do is we want to check to see if these things are, in fact, parallel lines. So we'll just say check if they're parallel. Because if they are parallel, we want to know that right at the beginning. If they're parallel, we either have situation 1 where they're parallel and distinct, or situation 3 where the two lines are coincident, and we shouldn't even bother checking for a point of intersection. So how can we check if these two lines are in fact parallel? What we want to look at are the direction vectors of our two lines. So for line 1, our direction vector is 2, 3. For line 2, our direction vector is 1, negative 1. And if these two lines are parallel, these direction vectors are going to be scalar multiples of each other. So there should be some way that I can multiply d1 by some scalar k. So instead of writing d1, I'll just put 2, 3 here and end up with 1, negative 1. Okay? And we can see by looking at this that this is not going to work. Okay? If k was 1/2, 1/2 times 2 would get me my x component of 1, but 1/2 times 3 isn't going to get me negative 1, so this is not going to work. So these two things are not parallel. And if these are not parallel, and we're working with two-dimensional lines, then we're on to case 2 here. These have to intersect at a single point. Nick?
Can you choose any scalar to check if they're parallel?
Well, what I chose here in terms of my scalar was the number that I knew would work for my x components. Right? So I knew that if k was 1/2, that's going to give me the x component I want. I mean, if I had chosen 3 here, it wouldn't work for my x, and it wouldn't work for my y either, so that really doesn't tell me anything. So pick one that's going to work for one of your components and see if it works for the other component. Okay. So if we know that these things are not parallel and we want to find the intersection, the way you want to work on this is not to work with the vector equations, but work with the parametric equations. So we'll take our two vector equations and we'll turn these into parametric equations. So for R1 here, our parametric equations are x equals 0 plus 2t, y equals 3 plus 3t. And for our second line, our x is going to be 0 plus 1s. So x equals 0 plus 1s. Our y is going to be negative 2 minus 1s. So we've got our parametric equations. Now, if these intersect in a point, we're looking for an ordered pair, x and y. And this ordered pair, x and y, has to satisfy both equation 1 and equation 2. What that means is that this x here from 1 has to be the same as this x here. Same thing for the y's. This y has to be the same as the y from equation 2. So if those x and y's have to be the same, we can equate the x equation from 1 and the x equation from 2. So we'll just say this is sort of step 3, equate x's and y's. So we get sort of two equations here. So if we equate our x's, we get 2t equals s, and we get 3 plus 3t equals negative 2 minus s. That's from our y's. So now we have two equations, two linear equations with two unknowns. Our unknowns are s and t. So this is the kind of system that we've been solving since grade 10. So we can go ahead and solve this for s and t. So the easiest way to do this one here is by substitution. So let's say that's step 4 here. Solve for s and t. So in this case, if we use substitution, we know that s equals 2t, so we're going to sub s equals 2t into my my y equation here. So I get 3 plus 3t equals negative 2 minus, and we sub in s, which is 2t, and then we just need to solve this thing. So I'm going to bring my 3 over to this side, negative 5. I get 5t equals negative 5. T equals negative 1. And then I can use my x equation to get a value for s. S equals 2t, so s is going to equal negative 2. So what do these s and t values mean? Well, these are the values of the parameters in these two equations that are going to give us the point of intersection. So the last step is to take these values of s and t, go back to our parametric equations, and find x and y. So let's just say use s or t to get x and y. So let's go back to equation 1, let's say. And our parametric equation for equation 1 was, scroll back up here, x equals 2t. That's going to be 2 times negative 1, or negative 2. Our y equation was 3 plus 3t. Sorry, did I do something wrong? Is it 0? Oh, okay. Let's just see. 3 plus 3 times negative 1. Yeah, it gives us 0. Okay. So that's going to be our point of intersection. Negative 2, 0 is our, we'll just say, point of intersection. That's not going to fit in there. So intersection. Okay. Now, I didn't have to use equation 1 there. I could have used equation 2, the parametric equation for equation 2, and then I would have been subbing in my value of s, and it should give me the same ordered pair, if this is in fact a solution to both lines. Okay. So 2 equations with 2-dimensional lines. Simplest case you're going to encounter. The next example, we look at what happens if we have 3-dimensional lines. And if we have 3-dimensional lines, there's another possibility. These lines can be parallel and distinct, they can be coincident, they can intersect at a point, or they can be what is called skew lines, which means they're not parallel, but they still don't intersect each other. You've got one line going off in this direction, the other line's going off something like this. Okay, so they just don't happen to intersect. So we want to be able to figure out whether or not these lines are skew lines. And this is only a possibility when you have a line in 3 dimensions. Okay? The way we approach the question is essentially the same. Okay? So, possible question here, find the intersection of these 2 lines. First off, let's check to see if these things are parallel. I'll tell you at the beginning that these are skew lines, so these are not going to be parallel, but every time you do the question, you should always check to see if these are parallel at the beginning. So you're looking to see whether you're comparing our direction vectors, is there some scalar k such that 1, 2, negative 3 is going to equal negative 2, 1, and 1. This one, we can see just by looking at it that it isn't going to work. If k was negative 2, I could get my x over here, but that's not going to give me my y's or my z. So these guys are not parallel, as we already knew. All right, step 2, let's get our parametric equations here. So for number 1, this time we're going to have 3 equations for each parametric in each set, because we now have x, y, and z. So our x is going to be 2 plus t. Our y is going to be negative 1 plus 2t. And our z is going to be 0 plus, or just negative 3t. Equation 2 is going to be, let's see, our x is negative 1 minus 2s. Our y is 1 plus s. And our z is 2 plus s. And let's just move this up a bit. So let's equate these things together here. So we get 2 plus t equals negative 1 minus 2s. Those are x's. Our y's give us negative 1 plus 2t equals 1 plus s. And our z's give us negative 3t equals 2 plus s. And what I like to do at this point is sort of straighten these up a little bit so that I always have in the same format every time. So I'm just going to collect those constant terms together and rearrange these so I just have t's on the left-hand side of my equation. So I'm going to have t equals negative 3 minus 2s. T equals, 2t equals 2 plus s. And my z equation is already good. It's negative 3t equals 2 plus s. So step 4, I wanted to solve for s and t. Now I have 3 equations with 2 unknowns. I actually only need 2 of these equations to solve for s and t. So what I'm going to do is I'm going to pick 2 and solve for s and t. So this is step 4. Pick 2, comma, solve for s and t. And the 2 that I'm going to pick are going to be these 2 right here. Because what I notice is that if I use elimination, I just have to subtract these 2, and I'll get those s's to cancel out. So let's do that subtraction there. 2t minus negative 3t is 5t equals 2 minus 2 gives me 0. S minus s gives me 0. And so my solution here is t equals 0. Okay. Now I want to go back and get my value for s, but I want to make sure that I use one of these two equations that I used to solve for t here. So I'm going to use my y equation here, which was 2t equals 2 plus s. I put in t equals 0, and then I get s is negative 2. So I've got my values of t and s. These values of t and s satisfy these two equations that I used to solve for them, my y equation and my z equation. If this is in fact, if these values of s and t represent a solution, they also have to be valued, they have to be valid for this third equation that I haven't used yet. So that's how I check to see if this is a good solution. I take my s and my t, and I sub them into this one that I haven't used yet. So I'll say step 5 here, check s and t in the other equation. And in this case, it was our equation that came from our two x components. So that was t equals negative 3 minus 2s. And let's sub in here. We got t equals 0. Sorry, that should be an s there. 3 minus 2s. Okay. And our s value was negative 2. So we have 0 on the left side and negative 3 plus 4, 1 on the right-hand side. Yeah, so 0 equals 1, which is bad when you get something like that. This is wrong. Okay, so if you get something that is a contradiction here, or it's an inconsistency, this is how you know that these two lines are skew lines. There is no value of s and t that is going to be a solution to all three of those equations that you got at the same time. So we can say, therefore, no point of intersection and if there's no point of intersection, either the lines are parallel or the lines are skew. We've already checked to see if they're parallel or not, so they have to be skew. Okay, there we go. Nick.
You have to use 1z always.
1z?
1z.
No. Use whichever ones are going to be easiest to solve. And in principle, like going back up here, I could have solved my x and my y using substitution, let's say. And I would get a different value of s and a different value of t, but then when I checked them in my z equation, I would still get something that gave me an inconsistency. So I would know that they were skew lines. Okay. All right, so let's flip it over here and take a look at next question on the back here. Okay. So here we're asked to determine the intersection of these two lines, and they give us the parametric equations. Now, when it just says determine the intersection, what it means is determine how they intersect. Are they parallel? Are they coincident? Are they skew? And if they do intersect in a point, find that point of intersection. So that's what's sort of understood in this question here. So let's give this one a try here. What should we do first?
Well, you can find out the directional vectors by just taking 1 and 1 and negative.
Yeah, we want to go for our direction vectors first. So we'll call this equation 1, equation 2. And as Nick said, our direction vectors come from the coefficient on this parameter. So for vector 1, our direction vector is 1, 1, negative 1. And for line 2, our direction vector is -2, -2, and 2. So what do we notice about these two direction vectors? Richard? Yeah. If I take d1 and I multiply it by -2, I'm going to end up with my second direction vector. So these two direction vectors are scalar multiples, which means the direction vectors are parallel, which means the entire lines are parallel. So therefore, these are parallel lines. And we want to find that out at the beginning. We don't want to go through the whole mess of trying to find a point of intersection if there is no point of intersection, possibly. So if we've got two parallel lines, we have to decide, are these lines parallel and distinct, or are they coincident? So how can we check if they are coincident? If they are coincident, any point that is on 1 is also going to be a point on line 2. So what we want to do is we want to pick a point that is on 1 and see if we can, to see if that point also satisfies line 2. So check if a point from 1 satisfies equation 2. Okay. If it does, they're coincident. If it doesn't, they're distinct. So what are the coordinates of a point that is on line 1? Well, we're going to 1, 2, and 0. It's on 1, okay? And and that just comes from our parametric equation. Here, here, and, well, there's a 0 in there. Okay? So let's check to see if this also satisfies equation 2. This is giving us a value of x, y, and z. Let's sub these into our parametric equation for 2. Or let's just deal with the x part first. What we're going to do is sub into 2. So from 2, this is 2 here, x is 3 minus 2s. Okay? If what we want is an x value of 1, we sub that in. 1 equals 3 minus 2s, and we can solve this for s. This gets us s equals 1. Okay? So if the value of the parameter in 2 is 1, s equals 1, then we get the x value that we want. That s value has to also give us the y value that we want and the z value that we want in order for this point to be on line 2. So let's check and see if that also works. Our y is, what do we have here? 4 minus 2s. And our z is -1 plus 2s. Let's try that s value in both of these equations. So if s is 1, y is 4 minus 2 times 1, y equals 2. Now, and we check back up here. Let's see, we're supposed to get a y value of 2. So that's good. And let's put s into our z equation. Z equals -1 plus 2, which is 1. We wanted it to give us a z value of 0. So this did not work. Okay. So what this means is that we don't have a value of this parameter s that we can sub into equation 2 that is going to give us the point 1, 2, 0. We have a value that works for x and y, doesn't work for the z. So what can we conclude from this? First off is that this point, 1, 2, 0, is not on line 2. What does that mean for our two lines? Are they parallel and distinct, or are they coincident? They are distinct lines. So we should just say, therefore, 1 and 2 are parallel and distinct. Okay. Yes.
Is it okay if I use the values of x, y, and z and just sub them into each of the equations instead of just taking the s value?
And then solve for s each time?
Yeah.
And comparing your s values?
Yeah.
Yep. Mathematically, it's the same thing. Okay? So that works just as well. Yep. You should come up with the same conclusion. Okay? So let's take a look at this last example here. We're given two lines, R1 and R2. We are told that they intersect at a right angle, so we want to show that they intersect at a right angle, and we want to find the point of intersection. So if they intersect at a right angle, we know there's going to be a single point of intersection here. We want to find it, but first we want to show that these guys are at right angles to each other. How are we going to show this right angle thing first, Richard? Yeah, so let's get our two direction vectors here. Yeah, we're just going to do d1 dot d2. Okay, dot product of our direction vectors is going to be 4, 8, negative 4, dotted with negative 1, 2, 3, which gives us negative 4 plus 16 minus 12, which gives us 0. So if the dot product of the direction vectors is 0, that tells us the direction vectors are perpendicular, so the lines are perpendicular. So therefore, we'll say R1 and R2 are perpendicular. Now we want to find the point of intersection. We know there's going to be one point, so now we just have to find it. So let's start by getting our parametric equations here. So for 1, we've got 4 plus 4t, and y is going to be 7 plus 8t, and z is going to be negative 1 plus, oh wait, negative 1 minus 4t. And what do we get for 2 here? 1 minus s. Our y is going to be 5 plus 2s. And our z is going to be 4 plus 3s. Okay. We'll equate our x's and y's and clean them up a little bit as we do this. So I've got to bring the 4 over to the other side. So I will get 4t equals negative 3 minus s. I will get, where did that 5 come from? 5 plus 2t, okay. So we've got to subtract the 7 from the 5 there, which is going to get us 8t equals negative 2 plus 2s. And in our last one here, we're going to have negative 4t equals 5 plus 3s. Okay. And let's number these. Our original two equations were 1 and 2, so we'll call this one 3, 4, and 5. We want to pick two of these and solve for S and T. Which two would you pick? The bottom ones. Why the bottom ones?
Just add like two ATs and then just subtract everything else. No, wait.
There's an even easier option.
The first one and the last one.
Yeah, 3 and 5, because here we've got 4t, here we've got negative 4t. We just have to add those, and those are going to cancel out. So let's use 4 and 5. Sorry, 3 and 5. So we get 4t equals negative 3 minus s, and negative 4t equals 5 plus 3s. Going to add these two, and we end up with 0 equals 2 plus 2s, or s equals negative 1. Okay, and then let's go back and use either 3 or 5 to calculate our value of t. So I'm going to use 3 here, I guess. 4t equals negative 3 minus negative 1. So 4t equals negative 2. T is negative 1/2. Now, if I'm worried that I've made a mistake finding s and t here, I can always check these in the equation that I haven't used yet. So I'm going to check using equation 4. Okay? At this point, if these both work in equation 4, then I know that I have a unique point of intersection. If they don't work in 4, that's telling me that my two lines are skew. Okay, so in that skew example, this is how I found out that they were skew lines. So let's put these guys into 4 and see what happens here. 8 times negative 1/2 is going to be negative 2 plus 2 times negative 1. And I get negative 4 equals negative 4. Woohoo! So we're on the right track here. So we've got our values of s and t. We just need to change these into x, y, and z. So we just take either s or t, sub them into one of our original parametric equations, and that's going to give us our point of intersection. So I'm going to use equation 1 here, and if I sub in equation 1, let's see, I need to use my value of t here. So if I sub my value of t into equation 1 for x, I get 4 minus 2. For y, I end up with 7 minus 4 is 3. And for z, I end up with negative 1 plus 2 equals 1. And I'm done. That tells me that 2, 3, 1 is my point of intersection. I didn't have to use equation 1. I could have taken my value of s, subbed it into equation 2, and that should give me the same point. So if you want to check if you've done it correctly, that's a good way of checking. And that's intersections of lines.